Example 1 is considering 3 functions and is asking us to answer 4 questions for each of the functions. We're going to start with figure 1. First, we have to decide what is the domain of the function in figure 1. If you notice, the function, as it gets really close to 0 from the right, the y values are going towards negative infinity. And as x gets really close to e, the y values are going towards 2. Now, at 2, we have an open circle. That means that the domain of the function doesn't include e. Also, the y-axis becomes a vertical asymptote because I do see that the graph is going towards negative infinity. So then that means that 0 will not be part of the domain. If you notice, there is no graph on the left, so then that means that negative values are also not in the domain of the function. So based on that, we are going to say that the domain of f will consist of everything from 0 towards e, but not including e. For this function right here, again, we see that there is no graph when x is negative. Everything begins when x is 0. The graph goes all the way from 0. It approaches 2. We seem to have an open circle here. However, if you continue upwards, you see that there is a closed dot. So all of a sudden, 2 is in the domain of the function. And then the graph continues all the way down until 6, and then it stops there. So this is telling us that the domain of the function consists of all x values starting with 0 and including 0 all the way to 6 and including 6. For the third function right here, if you notice, now we do have a few negative values up to negative 2. We go all the way down. We have an open circle here, meaning a removable discontinuity. However, when x is equal to 0, even though there is an open circle, we still have a closed dot right above. So then this is telling us that 0 is part of the domain. And then the x values continue all the way to 2. So then we're going to say here that the domain of f consists of all x values between negative 2 and 2, including negative 2 and 2, so including the endpoints. The second part of the question is asking us now to determine where the function is continuous. So going back to figure number 1, if you notice, this particular function is continuous everywhere in its domain, obviously except at e because we have a removable discontinuity, and at 0 because of the infinite discontinuity exhibited there. Therefore, we're going to say that we have continuity in the interval from 0 all the way to e. Again, 0 to e is the domain of the function. In this other figure right here, we see continuity at 0, right-hand continuity, and then all the way up to 2. However, at x equals 2, if you notice, there is a jump discontinuity. So then that means that the function is not continuous at 2. And then the function is perfectly smooth thereafter, stopping at x equals 6. So then we're going to say that we have continuity in the interval from 0 all the way to 2, union, and then 2 all the way to 6. Then when we go over to the third figure right here, we see continuity from negative 2, and then when we approach 0, we have a removable discontinuity there. So 0 will not be part of the interval. And then we have continuity all the way to 2. So then we are going to say over here that the function is continuous in the interval from negative 2 to 0, not including 0, and then 0 to 2. In part C, they're asking us to identify the absolute maximum value and the absolute minimum value if they exist at all in each of the functions. when we go to the first figure right here, we see that in terms of maximum, the y values are increasing as x approaches e. But as x approaches e, we never really reach to y equals 2, what really should be the maximum, because of this removable, this point that has been removed here. Then we practically have to say that we never really reach a highest value. Even if we claim that there is one, that this is the highest value, because this open circle is here, we can always argue that there's one that is even bigger and bigger and bigger, but we never really reach 2. So there is no absolute maximum value. In the other direction, the graph really approaches the y-axis asymptotically. So then these y values are getting smaller and smaller and smaller and smaller. But because they tend to negative infinity, there is never a minimum value that is achieved. So in this graph, we are going to have to say that there are no absolute extrema. So no absolute extrema. Please remember that extrema, saying extrema, that means, or absolute extrema, it means that there are no absolute minimum or no absolute maximum values. That's what this says. No absolute max and also no absolute minimum. Now, going on to figure 2. So in this case, let's see what happens. It seems as if indeed we do achieve a highest y value. In this case, we have a heavy dot. So indeed, there is an absolute maximum, and that happens precisely at x equals 2. And then when I go down on this linear part, we do achieve a lowest y value of -2. So here, yes, here we have an absolute maximum and we have an absolute minimum. So then we are going to say that the absolute maximum value happens to be 6, and it happens at x equals 2. And then the absolute minimum value is -2, and it happens at x equals 6. Then going on to figure 3 right here, the highest y value that is achieved by this graph happens to be 3. And in both cases, we have heavy dots, so 3 is part of the range of the function. Now, the lowest y value should have been 1, but unfortunately there we have an open circle. Then that means that again, we never reach 1. The y values, they get really, really close to 1, but we can never get there because this point right here has been removed from the graph. So then in this case, we are going to say that there is an absolute maximum. The absolute maximum value happens to be 3, and it happens when x is equal to plus or minus 2. But then there is no absolute minimum. The last part is asking us to identify any local extreme values. That really means to figure out if there are any local max or any local minimums. Now, when we find this local max or min, we will also specify the values of x where they occur. All right, I think that the easiest way to tackle this question is by remembering Fermat's theorem. If you remember, the theorem said that if a function has a local maximum or a local minimum at a particular value of x, then that value of x is a critical point of the function. It's a critical point. In other words, at this value of x, the derivative is equal to 0 or it is undefined. Now, to be a critical point, that means that this point has to be in the domain of the function. So we are going to be avoiding any values of x that are not part of the domain that we already specified here, here, and here. Again, format said that if a function has a local max or a local min at a value of x, then x must be a critical point. So I am going to be looking for places where the derivative is equal to 0 or where the derivative is undefined. When I look at this figure right here, I don't see any mountains or valleys indicating that my derivative is 0, and I don't have any sharp corners or places where the derivative is undefined. Now, if you're thinking about the endpoints, the function not being differentiable there, in pretty much all of these discussions, we avoid the endpoints from the point of view of differentiability, because at the endpoints, we can only talk about one-sided derivatives. So we don't want to be talking about a one-sided tangent line, put it that way. Therefore, it is okay, it is common to avoid the endpoints. So we're just going to be looking at what happens in the domain of the function, avoiding the endpoints. So in this case, we will say that there are no local extrema at all. All right, so no mountains or valleys, and no places where the function is completely not differentiable. Now, in this case, figure 2, again, avoiding the endpoints, let's see what is happening. I see a valley right here. So then this is indicating that I have a local minimum. If you notice again, if I consider a small neighborhood around 1, within that small neighborhood right here, 0 is the lowest y value achieved by the graph. So I already see that I have a local minimum. Now, do I have a local maximum? Well, I don't see a mountain, but I do see a place where the function is not differentiable. And then on the right of 2, the y values reach all the way up to 6, 6 being included. And then on the left of 2, in a small neighborhood on the left of 2, I never reach to anything that is bigger than 6. So I claim that 6 is a local maximum. So here I have both. I have a local minimum. The local minimum is going to be 0, and this happens when x is 1, and we have a local maximum. The local maximum is going to be 6, and this happens when x is equal to 2. Then we go to figure number 3. In figure number 3, let's see, again, avoiding the endpoints. We're looking for critical points. And for a critical point, you have to have completely a small open interval around that value of x. So in this case, look at this. I have a place here where my function is not differentiable. The derivative doesn't exist. So if I consider a small interval around it, let's say here and here, going up to my graph in this way, then within this small interval here, 2 happens to be the highest y value. Do I have a smallest y value? I'm hoping that you're noticing that we don't have anything else. We may have liked to say 1, but again, we have an open circle there because the y value at 0 is not 1, it is 2. So we only happen to have a local maximum. We don't have a local minimum. I am not seeing any more mountains or valleys or sharp corners or anything indicating that the derivative is undefined. So then that means that we only have a local maximum, and the local maximum happens to be 2, and we're going to have no local minimum. So writing that down, we have a local maximum. The local maximum is 2. And that happens precisely when x is equal to 0. And there is no local minimum at all. this question is asking us to use Rolle's theorem. Suppose that f of x is equal to this polynomial right here. They want us to prove that this polynomial has at most one real root. In other words, it cannot have more than one root. If we're going to have a root, the maximum is going to be 1, but no more than that. That's what we have to show. We cannot have 2 roots, 3 roots, 4, or anything else. The most that we can have is 1. So my suggestion is to first show that we have a root. Let's make sure that we at least have a root. And then we're going to show that this is the only root that we can have. It's like trying to get on a ladder, and we want to show that we can get to the first step of the ladder, but then we'll never be able to get to the second step or to the third or so forth. But at least let's climb the ladder and let's stay there. All right, so number 1, let us show that there is one root. So then, in order to do that, I'm thinking of the intermediate value theorem. I'm thinking of IVT. Now, a polynomial is continuous. So we know that f is continuous in its entire domain. And the domain of this polynomial consists of all real numbers. So f is continuous in the entire domain. What I want now is to be able to find 2 x values that are going to generate 2 y values, but one of the y values is going to be positive and the other y value is going to be negative, because then the IVT will guarantee the existence of an x-intercept. So if we now try, you can do this with a graphing calculator, or you can pick values and plug it into the formula. Let's say that I consider f of negative 1. So if I take f of negative 1 and I plug that into the function, I'm going to have negative 1/6 plus 1/2 minus 1 plus 1, and that will give me 1/3. So this is a number bigger than 0. Then let me consider f of negative 2 and do the same thing. When we do that, we're going to have negative 8 divided by 6 plus 4 divided by 2 minus 2 plus 1. And then simplifying, that will give me negative 1/3. And now this is less than 0. So f of negative 1 is positive. F of negative 2 is negative. So this implies, by the intermediate value theorem, that implies that there exists, for example, a number c, a value c, in the interval from negative 2 to negative 1, such that f of c is equal to 0. This is what the IVT allows me to conclude, since the function is continuous in the entire domain, and since one of the y values is positive and the other y value is negative. So I know that there exists a number c in negative 2 comma negative 1, such that f of c is equal to 0. So this is saying we found a root, we can climb on the first step of the ladder. Now we want to make sure, however, that we're not going to go higher on the ladder, that indeed this is the only solution, this is the only root of this polynomial. So in order to do that, we are going to go ahead and proceed through contradiction. So we will say, suppose not. I'm going to do the opposite. Suppose not. In other words, suppose that f has another real root. As if we are misbehaving. We're assuming the opposite of what they want us to show. Let's say that it has a real root at x equals a. So if the polynomial has a root at x equals a, that implies that f of a is equal to 0 as well. So all of the sudden, look at this. F of a is equal to 0 and f of c is equal to 0. So because we have continuity involved, remember that f is continuous. F is continuous in the entire domain. So then that means that f is continuous in the interval AC. So f is continuous in AC. Now, depending as to which one is bigger or smaller, I'm going to say in AC, or why don't we say CA? Because we don't know whether A is bigger than C or vice versa. But we know that F is continuous in these intervals. And if F is continuous and we have that F of A is equal to 0 and F of C is equal to 0, then by Rolle's theorem, we know that there exists some other number k in the open interval AC or the open interval CA such that f prime of k is equal to 0. This is supposedly what Rolle's theorem allows us to conclude, given that we have this satisfied and we have this satisfied. Then Rolle's theorem says that the function, the derivative at some number k must be equal to 0. So what I want to do now is to make sure that this is indeed true. Is it true that for my given function, the derivative is equal to 0 at some k? You have to remember that we decided to suppose the opposite. So what I want now is to find a contradiction. I want to find a flaw in this assumption right here. Based on this assumption, this is true, and this is true. Let's see if that's the case. So now let's go ahead and find the first derivative. Let's differentiate. So f prime of x will be equal to 3x squared divided by 6 plus 2x divided by 2 plus 1. Simplifying, this will be x squared divided by 2 plus x plus 1. Then I'm going to go ahead and factor 1/2 out, and when I do that, I'm going to get x squared plus 2x plus 2. And now, if you take the time to examine this quadratic, the discriminant of that quadratic, if you remember that discriminant is equal to b squared minus 4ac, the discriminant ends up being -4. And whenever a quadratic has a negative discriminant, that means that this quadratic is will never intersect the x-axis. So this quadratic has no x-intercepts. And because the quadratic opens upwards, right, this quadratic will open up like this, it is going to be completely above the x-axis. That's the meaning of having no x-intercepts and opening up. So it's going to be completely above the x-axis, meaning that then our conclusion will be from this analysis that f prime of x can never be equal to 0. So then how is it possible that here we said that there is a k such that f prime of k is equal to 0? And here, when we find the first derivative and we work it out a little bit, we get to a point where the quadratic in the first derivative never equals to 0. So this quadratic is never equal to 0, which really means that the first derivative is never equal to 0. And that now nicely will give us a contradiction. So practically then, this part over here that I'm highlighting in yellow becomes the contradictory statement. We reached a contradiction by making this assumption right here. You see, when we made this assumption, that assumption led to a contradiction. So our conclusion here, based on this contradiction here, is that f only has one real root. And this is the one that was guaranteed here above by the intermediate value theorem. Let's quickly write that down. So therefore, f only has one real root. When we assumed that it had more, we got to a contradiction that told us that that assumption was incorrect. And again, repeating myself, I'm talking about this assumption right here. By making this assumption, we got to this problem. We got to see that no, there isn't a single value of x such that the derivative is equal to 0. So then that means that this cannot be assumed, because if it's assumed, we get to something that is inconsistent. So then that means that there's only one real root. Example 3 is asking us to find any critical points of the following functions. We're going to go ahead and tackle the polynomial first. Remember, to find critical points, we want to be able to find the first derivative, and we want to see where the first derivative is equal to 0, and also where the first derivative happens to be undefined. So that's the task. So then starting with A, let's find the first derivative of the polynomial. F prime of x is going to be equal to 3x squared minus 12x plus 9. And then factoring 3 out, that will give us 3x squared minus 4x plus 3. And then factoring the quadratic, this will be x minus 1 as the first factor and x minus 3 as the other factor. So then this is f prime of x. So then to find critical points, I am going to be using CP for critical points. I have to see where is f prime of x equals to 0, if at all. In other words, 3 times x minus 1 times x minus 3, when will this be equal to 0? Then I just solve that equation. That implies that x minus 1 is equal to 0, or x minus 3 is equal to 0. In other words, x is equal to 1 and x is equal to 3. So then so far, as if we have found two critical points. Now remember, by definition, however, a critical point has to be in the domain of the function. So we have to check whether 1 and 3 is in the domain of the function. And the good news there is that yes, it is, because see, the domain of my function f consists of all real numbers, from negative infinity to positive infinity. So then 1 and 3 are perfectly valid critical points. Now, we have to also consider if the other part will be, is f prime of x undefined at all? And the good news, or another good news here, is that polynomials are defined everywhere. And beautifully, they are completely smooth. They don't have any sharp corners. There are no jump discontinuities, no removable discontinuities. So then that means that I can draw a tangent line anywhere in the domain of this function. In other words, f prime of x is never undefined. That means that these are the only critical points. So as a conclusion, I'm going to say here, therefore, the critical points are going to be x equals 1 and 3. So these are the two critical points that I found. we will now do something very similar for part B, g function. Now, the first thing that I'll do right away is to figure out the domain of my function g. If you notice, the only issue here happens to be with x in the denominator. In the numerator, we have the cube root because of these three right here, and cube roots are defined everywhere. So the only issue here happens when x is equal to 0. In other words, 0 can never be part of the domain because division by 0 is undefined. So we're going to say here that the domain of g happens to be all values from negative infinity to 0, but not including 0, and then union from 0 to positive infinity, again, not including 0. Then we're going to go ahead and continue by finding the first derivative. Now this is just applying the quotient rule. I'm going to go ahead and skip that work. I will assume that by now you can handle that nicely. When we find that derivative, again using the quotient rule, we find that g prime of x is going to be equal to 6 minus x divided by 3x squared times x minus 2 to the 1/3. That becomes our derivative. So now we need to figure out when will this derivative be equal to 0, and then later on, when will that derivative be undefined? So let's do the first one first. So number one, when will g prime of x equal 0, if at all? Because we have a fraction, the only way that a fraction can be equal to 0 is if the numerator is equal to 0. I don't want my denominator equal to 0 as well. Remember, 0 over 0 is indeterminate. That makes no sense. So just when the numerator is equal to 0. So this is true as long as 6 minus x is equal to 0, which really means that x is going to be equal to 6. Now, before I declare this a critical point, I have to make sure that 6 is in the domain of my function. So I'm going to go back to the domain over here, and I see that 6 is a valid number. It is in the domain, so I'm super happy with 6. Now I have to figure out, are there x values that will make my derivative undefined? And because that derivative has a denominator with variables, there are x values. If the denominator is equal to 0, then the derivative is going to be undefined. So the derivative will be undefined when 3x squared times x minus 2 to the 1/3 is equal to 0. And what does that mean? That means when 3x squared is equal to 0, or when x minus 2 to the 1/3 is equal to 0. So now we're just going to go ahead and solve each equation separately. So then when x is equal to 0 in this case, and here, remember the way to get rid of this exponent is by cubing, doing the opposite of the 1/3. So then that means when x minus 2 is equal to 0, when x is equal to 2. Now, however, I want you to go back and look at the two possible candidates for critical points. Critical points have to be in the domain of the function. 0, if you remember, going back over here, was excluded from the domain. So 0 will not be a valid critical point, out. And then what happens with 2? 2 is perfectly valid. So that means that we found two critical points. Conclusion, we're going to say, therefore, the critical points are x equals 2 and 6. These are the two critical points. Example 4 is asking us to find the absolute maximum value and the absolute minimum value of each of the following functions, f of x and g of x. in order to do this problem efficiently and also very quickly, we want to be able to use the extreme value theorem, the EVT. The extreme value theorem, if you remember, said that if a function is continuous in a closed interval, AB, then we know for sure that it has an absolute max and an absolute min. But on top of that, the theorem says that this absolute extrema happens at the critical points or at the end points. So again, the critical points or the end points. So that's where we have to search for these values. Notice that in part A, I have a polynomial. You may already notice also that this polynomial is the same polynomial that we had in the last example, in example 3. I am recycling the same functions because we already found the critical points and I don't want to have to do all that work again if I choose new functions. So I'm using the same functions as in example 3. That means, if you remember, that the critical points that we found there were 1 and 3. So all that I have to do now in order to apply the intermediate value theorem is to consider the y values at these points. That means at the critical points and the end points. Now, the critical points of the first polynomial were 1 and 3. You can see them right here. However, only 1 is in the closed interval 0 to 2. So then that means that 3 will not be considered here because 3 is not in the closed interval. So we will then compute f of 1, and then we will exclude 3 again because 3 is not in the closed interval. And then we're going to go ahead and compute f of 0 because 0 is the left endpoint. And then f of 2 because 2 is the right endpoint. So the the extreme value theorem says that one of these is going to be the absolute maximum and one of these is going to be the absolute minimum. Again, because that's going to happen at the critical points or at the end points. Again, we excluded 3 because 3 is not in the closed interval. So now we're just going to go ahead, take 1 and plug 1 into every x that we have in that function. For example, 1 minus 6 plus 9 plus 2, that's going to give us 6. Same thing with 0, that will just give us 2. And same thing with x equals 2. When we plug in x equals 2, we get 4. So then from here, we see that 6 is the highest y value. That means that this is the absolute maximum value. And that happens exactly when x is equal to 1. And then we see that 2 is the smallest y value. So this is the absolute minimum value. And that happens when x is equal to 0. So then if you notice now that x equals 1, exactly here, x equals 1 is a critical point. So we achieve one of the absolute extrema at a critical point. And then x equals 0 is an endpoint. So the other absolute extrema is achieved at one of the endpoints. So whenever we have a closed interval and the function is continuous in a closed interval, the way that we find for absolute extrema is by calculating the critical points and then evaluating the y values at the critical points that lie in the closed interval AB and also at the endpoints. Let's go ahead and pretty much repeat the process with the other function, with g of x. So now for g of x, the closed interval happens to be 1 and 10. And if you remember again, the critical points are 2 and 6. Now both 2 and 6 lie in the interval from 1 to 10. So that means that we have to go ahead and consider g of 2. We will consider or compute g of 6, and then g at the endpoints, g of 1 and g of 10. Plugging this into the function, we get 0 for g of 2. For g of 6, we actually get an approximation of about 0.42. G of 1 is equal to 1, and g of 10 is about 0.4. So now we can see that 0 is the smallest y value. So this becomes the absolute minimum. And that happens precisely when x is equal to 2. And if you notice nicely that x equals 2 is precisely a critical point. So that's where we have one of the absolute extrema. Then we look for the the largest y value that we have. And the largest y value happens to be 1. So then that means that 1 is the absolute maximum. And that happens precisely when x is equal to 1. And x equals 1 is not a critical point. X equals 1 is the left endpoint. So the other absolute extrema happens at the left end point. So this is exactly how we put the extreme value theorem in practice. Given a continuous function in a closed interval AB, we find the critical points, and then we evaluate the function, the y values at the critical points and the endpoints. We look at all of the values and we pick the largest y value. That's going to be the absolute maximum. The lowest y value is the absolute minimum. You do have to be careful that when you look at the critical points, though, you only choose the critical points that lie in the closed interval AB. In this problem, they're asking us to find the absolute maximum and the absolute minimum value of this piecewise function. This is now the interesting part. We're essentially doing the same thing as before, finding absolute extrema. But here now there is a spice. We have a piecewise function. Now, the first thing that we have to do if we're thinking of the extreme value theorem is again to check for continuity. We have to make sure that f of x is continuous in the interval starting with 0. So 0 is going to be the left end point, and 3 is going to be the right end point. Because this is a question about continuity, we already talked about continuity quite a bit in previous chapters. I am going to leave that up to you. You're going to go back to the basic definition of continuity and make sure that this definition is fully satisfied. I'm going to make a note over here, though, that the first thing that we need to do in order to have a perfect analysis is to check that f is continuous. F is continuous in the closed interval 0 to 3. And in fact, it is continuous. Continuity checks nicely in that interval. Then what I want to do now is to find the critical points. Again, I'm trying to use the extreme value theorem. For that, I need critical points. So, because I have two pieces here, I am going to consider the derivative in the first interval and then the derivative in the second interval. So that means that in the first interval, from 0 to 2, right here, within this interval, the derivative, in other words, f of x is going to be equal to 2x minus 1. So then that implies that the derivative of this function is going to be equal to 2. But because it is equal to 2, then this derivative is never equal to 0. Then that means that we don't get any critical points from the first piece of the piecewise function. All right, now let's go on to the other piece. That is going to go from 2 to 3. So actually, what I should do here is to put open because 2 is technically not included in the second piece. So from 2 to 3. So in this case, we know that the function f of x is equal to x squared minus 5x plus 9. Differentiating this function, that will give us 2x minus 5. Now here, I may be able to get critical points. I'm going to go ahead, take 2x minus 5 and set that equal to 0. That means that 2x is equal to 5. Therefore, x is equal to 5 over 2. And then when I check 5 over 2 to see if 5 over 2 is in my interval right here, I notice that 2.5 is precisely between 0 and 3. So then this is a valid critical point. Now I have to figure out if my function is not differentiable somewhere in the interval 0 to 3. Well, it is always differentiable in the first interval. It is always differentiable in the second interval. So if there is a potential danger for this function not to be differentiable, it will happen at 2, that transition point. Notice right here, exactly when the function transitions from a line to a quadratic, to a parabola. That means that if we want to be super careful, we have to go and check whether f is differentiable at 2. And because it is a piecewise function, 2 is the transition point, you're going to go back to the basic definition of a derivative, the limit definition. You cannot apply techniques of differentiability at x equals 2. This is exactly where the transition takes place. So we're going to go back to basics. However, again, I'm going to leave that up to you to check. It's a quick check by using the limit definition, one of the two formulas that expresses the derivative as a limit. So I'm going to make a note over here that you will check whether f prime of x exists. And it turns out actually that f prime of x does not exist at x equals 2. It doesn't exist. So then that tells me immediately that 2 is a critical point. All right, so I'm going to go ahead and circle this, x equals 2, because a quick check, 2 is right there in the domain of the function from 0 to 3. So it's a valid critical point. So now we are ready for the extreme value theorem. So the extreme value theorem, EVT. We're going to go ahead now and compute f of 5 over 2. We will compute f of 2, and now f at the end points, f of 0 and f of 3. Using the function, f of 5 over 2 will be equal to 5 over 2 squared minus 5 times 5 over 2 plus 9. If you're wondering why I am doing this, well, 5 over 2 is 2.5. 2.5 is between 2 and 3. That means that we are working with the second piece of the function. So I take the second piece, which is the quadratic, and substitute 5 over 2 in place of x. Now, when I do the calculations, I should get 11 over 4. Then we're going to go ahead and do the same thing with f of 2. When x is equal to 2, we are dealing with the first piece of the function. So then that's going to be 2 times 2 minus 1. That will give us 4 minus 1, which is going to be equal to 3. Now, f of 0. 0 happens to be again in the first part of the function. So then 2 times 0 minus 1 will be equal to 0 minus 1, negative 1. And then we need f of 3. 3 is on the second part of the function, on the quadratic. So then 3 squared minus 5 times 3 plus 9, that will give me nicely 3. So the absolute maximum, now I'm going to go ahead and look for the highest y value. So then the highest y value that I see here is 3, and also here 3 repeats. That happens when x is equal to 2 and when x is equal to 3. So then this is going to be over here the absolute maximum value. I'm going to do the same thing over here. This is going to be the absolute maximum value. It's exactly the same value. And this happens precisely when x is equal to 2. And here, this happens when x is equal to 3. Now I need the absolute minimum. Well, the absolute minimum value happens is negative 1, which takes place when x is equal to 0. So I'm going to say over here, absolute minimum value is negative 1, and that happens precisely when x is equal to 0. So again, two things that I would love for you to do is to make sure that you settle the continuity. That will be a great way to review continuity. And then to settle that or investigate or somehow show, let's say, that f is not differentiable at x equals 2, which again is a wonderful way to review the basic definition of a derivative. The extreme value theorem can also be applied to word problems. The math behind it, the idea behind it is the same as a more algebraic problem versus a word problem. Let's read it. A rain gutter is to be constructed using a piece of aluminum 12 inches wide. You can see that piece right here. After marking a length of 4 inches from each edge, the piece of aluminum is bent up at an angle theta. So you can see over here how these two little pieces at the end are bent by the same angle theta, by the same amount. The area of a cross-section of the opening expressed as a function of theta is given by this expression. So the area of the cross-section right here, this brown part. They're asking us here to find the angle theta that maximizes the area. This is another way of saying find the value of theta that will somehow generate an absolute maximum. So we're really looking for an absolute maximum, just like the previous example. Only that somehow there's a story behind the problem. Let's make sure that we keep in mind that this is the closed interval. Theta ranges from 0, including 0, to pi over 2. The first thing that I'm thinking here is the extreme value theorem. But if I want to use the extreme value theorem to find my absolute maximum, I am going to first show that the function a of theta is continuous in the closed interval. Because remember, if I don't have continuity, the extreme value theorem doesn't work. So number 1 is to show continuity. However, this is trivial because a of theta is just pretty much only consists of trigonometric functions. There are no denominators. So then that means that the entire function is going to be continuous. So we are going to say over here that since sine theta and cosine theta are continuous, then we know that cosine theta plus 1 is also continuous. That implies that a of theta, which is now the product of these two expressions is also continuous. Is also continuous in the interval from 0 to pi over 2. So a brief discussion about continuity, nothing deeper than that. So that takes care of our continuous discussion here. Now let's go ahead and find critical points. So this is the second thing that I want to do, because remember, I want to apply the extreme value theorem. So I need critical points. In order to find critical points, I will first re-express the function. Before differentiating, I will take a of theta and re-express it as 16 times sine theta times cosine theta plus 16 sine theta. And then I will rewrite this part right here as, let's write it as 8 times, and then 2 times the sine of theta times the cosine of theta. Then the rest, the same as before, plus 16 sine theta. And the reason why I wanted to rewrite it as 8 times 2 is because now this over here, this expression right here, using a trig identity, will simplify to sine of 2 theta. So now I can write this nicely as 8 times sine of 2 theta plus 16 sine theta. And if you're wondering why am I doing that, that's just because I want to make my differentiation a lot simpler. I wanted to avoid having to use the product rule and all that stuff. You don't have to do that, however. I just think that may be a little bit nicer when it comes to differentiating. So then, let's go ahead and now finally find the derivative. So a prime of theta will be equal to 8 times cosine of 2 theta, now applying chain rule, times 2 plus 16 cosine theta. I'm going to go ahead now and simplify just a little bit, and that is going to give me here 16 times the cosine of 2 theta plus 16 times cosine of theta. And nicely now, I have my derivative. So now that I have my derivative, I have to investigate two cases. When is my derivative equal to 0? And when is it undefined? You can already see that because my derivative consists only of the sum of cosines, it is never undefined. This is always defined. So this is going to always be defined. That means that the only critical points, if there are any, are going to happen by setting that derivative equal to 0. So let's go ahead and do that nicely over here. I'm going to go from the left here of the screen. So when will a prime of theta equal 0? So let's take 16 cosine of 2 theta plus 16 cosine of theta and set that equal to 0. Now, I'm going to have to go now and use the identity for cosine of 2 theta. This identity, and if you forgot, you can derive it or just quickly look it up. That identity is equal. One of the identities is 2 cosine squared theta minus 1 plus 16 cosine theta equal to 0. And then simplifying a little bit, we're going to have 32 cosine squared theta. Then over here, we are going to have plus 16 cosine theta. And then minus 16 equals to 0. Then I am going to get a common factor out. So that's going to be 16 times 2 cosine squared theta plus cosine of theta minus 1 equals to 0. And if you notice right here, I have a beautiful quadratic. So I will see if this quadratic is factorable. That means 16 times, and then trying to factor the quadratic, we are going to have here 2 cosine theta minus 1 times cosine of theta plus 1 equals to 0. So then that implies that cosine of theta is going to be equal to 1/2, and over here cosine theta is going to be equal to -1. So now we have to see, we have to solve these mini equations right here. Remember that the interval that we're working with is between 0 and pi over 2. So then we have to figure out when is cosine theta equal to +1/2. And within this interval right here, that is going to happen when theta is equal to pi over 3. Whereas the other equation that we see right here, cosine theta equals to -1, is not going to have a solution because we are again in the closed interval from 0 to pi over 2. And in this interval, cosine theta never equals to -1. So then in this case, right here, we are going to have no solution at all. That implies we're going to say here that theta equals pi over 3 is the only critical point. And again, pi over 3 is a valid critical point because pi over 3 is in the interval from 0 to pi over 2. So what we are going to do next is to now apply the extreme value theorem by considering a of pi over 3 and then a of 0 and a of pi over 2. Here I have a of pi over 3. We're going to take pi over 3, substitute pi over 3 into the function itself, use our calculator to compute the result. And that result should be approximately 20.785. A of 0, again, when we plug 0 into the equation or the expression for a of theta, we end up getting 0. And when we plug in pi over 2, we end up getting 16. Now you can notice that the highest y value that we achieve is precisely 20.785, and that happens when theta is equal to pi over 3. They didn't ask for the minimum value, the absolute minimum. They ask for the value of theta that will maximize the area. So, therefore, we will say here, therefore, the area is maximized exactly when theta is going to be equal to pi over 3.